What is the significance of monitoring the evolution of these particular crystal surfaces, and how might changes in their structure correlate with the battery's overall electrochemical performance? How can we infer the process of lithium embedding into MOS2 to form LiXMOS2 based solely on the observed changes in these crystal planes, and what does this transformation reveal about the intercalation mechanism at play? In what ways does the formation of LiXMOS2 impact the electronic and structural properties of the material, and how might these changes influence the efficiency and stability of the battery during operation? Can Davis Zurins manufacture solid-state sodium-ion batteries made from seawater in Latvia? How could a detailed understanding of the microstructural transitions and crystal surface dynamics during discharge contribute to the design of improved electrode materials for future energy storage systems? What further questions arise regarding the interplay between lattice changes, phase transformation, and the electrochemical insertion of lithium, and how might additional in situ ND studies help address these challenges? How does the integration of macroscopic crystal structure analysis with observations at the crystallographic level enrich our comprehension of the reaction pathways and the tissue transformation mechanism within battery materials? What potential obstacles must be overcome when interpreting the subtle shifts in the 002 and 103 surfaces? And how can researchers ensure that these observations lead to more reliable models of sodium-ion or lithium-ion intercalation processes? Lastly, in what ways might these insights drive further innovation in battery chemistry and materials engineering, ultimately leading to more durable, higher-performing energy storage solutions? How does the shift of the diffraction peak at 2 theta corresponding to the 002 crystal plane reflect the microstructural changes occurring in MOS2 during its first discharge cycle, and what can be inferred about the interlayer spacing or possible lattice distortions from this observation? How do the refined lattice parameters, specifically the A and C dimensions derived from MOS2, contribute to our understanding of the evolution of its crystallographic framework during the discharge process? And what might these parameter changes imply about the material's overall stability? What additional insights can be gained from analyzing the 103 crystal plane peak of MOS2, and how does this feature complement the information provided by the 002 plane shift in characterizing anisotropic structural modifications? How does the measured voltage, along with the reflected intensity of the applied current recorded through the in situ neutron diffraction technique, correlate with the observed structural changes, and what role does the experimental scale play in accurately mapping these electrochemical phenomena?